Okay, so these lectures are not really going to be lectures about control theory. They're going to be lectures about some mathematics that can be used for formulating certain problems in control theory. But the lecture today the first part of it at least, will be a little bit about control theory, just to try to give some motivation for what we're doing. So this will be mostly of interest or any value for people who have no background in control theory. There's a couple here. But for those of you who do, perhaps there'll be a different way of thinking about things that will motivate what we're going to do as we go along. Okay. So in control theory, or at least the kind of control theory that I'm going to make reference to, you're looking at dynamical processes governed by equations like this. X, for our purposes, will be a curve in a manifold. U is going to be in some set C, which is a control set. For what we're going to be doing, C will be a topological space. Okay, and F is going to be a map from M across C into Tm with the property that f of x u is in the tangent space at x. Okay, so that's a control system for our purposes. And so the idea is, again, for those of you who have no background in control theory, you prescribe u as a function of t in some way, or possibly also u might be a function of x and t, or various other kinds of things. And then once you specify u, then this just becomes a time-varying vector field, and you solve the time-varying vector field, you get trajectories of your system. Okay, so the idea is you start at some point, maybe. You choose a control, u, let's just say that u is a function of t, and it has to have some properties, and we'll get fussy about those kinds of things a little bit later. But once you plug u in here, you have a time-varying vector field, you solve the time-varying vector field for some time, you get a trajectory like that in x. Okay, change your control, you get another trajectory, and so on. And so control theory, in some sense, is the study of these trajectories that you get like that. Okay, so let me talk a little bit about some standard problems in control theory, because these are going to be the things that I'm interested in developing a framework to investigate. Okay, one basic problem is controllability, and I will not be precise about any of this because it's really kind of not the point here. Okay, we can do. Okay, so controllability means this. So let me first just say that I have this point x naught like so, and I run u over some class of controls, maybe bounded measurable functions, bounded meaning taking values in some compact set. And so you run u over all such controls, and you measure all the endpoints here, and maybe these end at some time capital T. Okay. The set of all endpoints of these trajectories, we're going to write x like that. Okay, so this means the reachable set from x naught in time t, and then you also have the reachable set in time at most t, meaning that you just consider the union of all these guys between 0 and capital T. Okay? All right, so controllability has to do with studying what these reachable sets look like. Okay, so what does that look like? So some properties of reachable sets might include things like, a very, very basic one is, does the set of reachable states from x naught in time t, is that equal to all of m? Okay, you've got some sort of global controllability. Okay. Another kind of thing would be, x naught lie in the interior of the reachable set. That's some kind of local controllability, okay? And so controllability questions are very fundamental in control theory, because before you can answer any kinds of practical questions, practical question might be, can I steer my system from x naught to some other final point x1, you should know if that's possible. So controllability is kind of the existential problem associated with, can I go from here to here? Okay, so you really want to describe the character of this reachable set, right? And I will say not much more than that about this. Okay, a sort of problem that seems dual, and I don't know, maybe it is dual in some sort of way, but not that we understand very well. But it's stabilizability. So stabilizability, controllability means you start at x naught, you go like this. Okay, stabilizability is kind of the opposite problem. And so one way to phrase stabilizability is, can you design u as a function of state and time so that when you plug this u, which is now a fixed function of state and time, into this differential equation. Okay, so that means you're looking now at, Okay, so that now is just a differential equation, right? U has been prescribed as a function of x and t. Okay, so it's just a differential equation. Okay, so we're going to look at some point x naught. Is x naught a stable equilibrium point? Okay, that's stabilizability. Okay, so you can relatively easily imagine that this is a practical sort of a problem. You have some equilibrium point. The classical thing that people think about are and that you see in control labs all over the world, is a cart on a pendulum. So the cart slides back and forth, there's a pendulum on top of it, and you get to shake the cart. Can you make the pendulum stand upright? Okay, so that means finding a specific u as a function of state and time that achieves that. Okay, so stabilizability is kind of the existential version of that sort of practical problem. Okay, so these are, you should think of these as being structural attributes of a control system. Okay, so if someone gives you a problem, you'd like to know, does it possess either or both or neither of these properties? Okay. Now these are hard problems. In fact, I think it's fair to say that we're a million miles from understanding either of these things in any kind of generality. Okay, tons and tons of work have been done. So let me maybe just chatter a little bit about the nature of the work here. So if you know something about dynamical systems, you know that stability of equilibrium in dynamical systems, there's a Lyapunov theory for that. Well, there's also a Lyapunov theory for stabilizability. That theory is pretty comprehensive and complete. The problem with the Lyapunov theory of stabilizability is that what it does is it replaces one unanswerable question with another one. So the one unanswerable question is the system stabilizable? The other unanswerable question is, does it possess a Lyapunov function? Okay. So Lyapunov functions are good if you have them for design purposes, but existence of them is no easier than deciding whether a system is stabilizable or not. Okay. Controllability. So a large quantity of the work in stabilizability has been in this sort of Lyapunov direction, because it is practical. When you have a Lyapunov function, it helps you design control laws. Okay, so that's good. Controllability, on the other hand, has been studied largely from a geometric point of view. And I would say maybe the genesis of geometric nonlinear control theory was in the problem of controllability in some sense. Okay, so really these two very important issues that somehow, if you are coming at this from a naive and therefore maybe a naive point of view, therefore maybe having a fresh set of eyes, these seem like they should be related. Really, all you're doing is changing the directions of the arrows. Okay. From controllability to stabilizability, they seem like they should be related. If you look at the literature for these problems, you will see no relationship really between them. They're studied in really completely different ways. And so what I aim to develop in this talk is a framework for studying these kinds of questions, and maybe also understanding relationships between these. All right. Okay, so what are the impediments to doing this? Okay, well, there is an impediment here. Okay, and let me try to describe that with an example. So I will consider two systems. That's one. That's two. Okay? All right, so these are very simple systems, of course. For those of you who know what the words mean, these are control affine systems. They're even bilinear. Okay? These are bilinear control systems. All right? Okay, so it's relatively easy to see, really they differ in line 2. It's relatively easy to see that the set of trajectories for these two systems are the same. So if you have a control U that gives you some solutions over here, U plus or minus 1 will get you the same solution over here. So there's an exact trajectory correspondence between these two systems. Yeah.
When you say you have exact same trajectory, you mean for the same U or for the...
Of course not.
Of course
Yeah,
not.
yeah,
So that's
yeah. But I'm interested in trajectories.
Yeah.
Yeah. Okay. Okay. So as if you're only interested in trajectories, these guys are the same. So they should somehow behave in the same way. Now, so to illustrate what I'm talking about, we'll think about stabilizability. So actually, we can think about either controllability or stabilizability. And let's suppose we're interested in looking at the equilibrium point at the origin. Okay. Now, the thing that we teach our undergraduates when we teach them to do nonlinear systems is really the only thing we teach them is to linearize. Okay. So what you do is you just take Taylor series of these things, and you keep the first order terms in both x and u. Okay. Now, that's just standard textbook Jacobian linearization. Okay. And you will find this technique in every textbook on nonlinear control theory. All right, and so, but the conclusion that you get here is when you linearize this guy, so let's call this one 1, this one 2. Okay, so the idea is in linearization, is you linearize and then you look at the properties of the linearized system, which is, of course, a linear system. So you study the controllability of the linear system and the stabilizability of the linear system, and then you pray that there's some sorts of connections you can make between the controllability of the linearization and this, or stabilizability of the linearization, and that for the actual system. Okay? So, when you look at the linearization, the linearization of 1 is neither controllable nor stabilizable. And so, there's sort of standard theorems which say, if the linearization is controllable or stabilizable, then the nonlinear system is locally. Okay, so those terms don't apply here. And two, okay, has a controllable linearization, which you can see very easily. When you linearize, that just goes away. And that's, if you know linear control theory, that linearization is controllable. It's one of the standard forms for controllable systems. Okay, and so therefore, for this one, you have a controllable and stabilizable linearization, and so you can use, for example, theorems about connections between linear and nonlinear systems via the linearization to assert local controllability for that guy. Okay? So the punchline here is this, is that Jacobian linearization is not, and I'll say just vaguely what I mean here, it's not well defined in that it depends on more than just trajectories. Okay, and if, you know, so the way to think about this example is this. Don't try to figure the example out. That's too easy. This example is, as far as I'm aware, the very, very, very simplest example that you can possibly come up with to illustrates the phenomenon that I'm after here. It's maybe too simple. Okay? So in other words, you can figure this out. You know how to rectify the seeming incompatibility between these two conclusions here kind of by hand. Okay? But that's not what I'm asking. What you should ask yourself is this. What is the correct definition of linear controllability or linear stabilizability so that these are really two representations of the same system, right? So that the controllability of the linearization will be the same for both of these. Okay? That's the question that you should be trying to answer. Okay, does that make sense? Okay, so this is just the most elementary kind of example, but if you look at the literature on geometric control theory, it's filled with examples and ideas and methodologies and theorems which have this kind of phenomenon, where two different representations of the system will react with the theory or methodology in incompatible ways. And I don't wish to explore this in a lot of detail, because it's not exactly the point here. But take my word for it. Okay, and so by geometric control theory, I mean control theory which is governed by the equations that I just erased here, the x dot is equal to f of x comma u type systems, okay? Now the problem here, so why did people study geometric control theory? People studied, as opposed to, so now what's geometric control theory? So geometric control theory means your states live in a manifold, okay? Why did people begin to study geometric control theory instead of just doing control theory on open subsets of Euclidean space, which is kind of classical nonlinear control theory? So what's the value of geometric control theory? The value of geometric control theory is that you ought to be working with things which are coordinate independent, okay? So it forces you into talking about things which are useful, like vector fields and Lie brackets and stuff like that. Okay, if you stick to sort of the, kind of a more analysis-y kind of nonlinear control theory where your states live in a Euclidean space and you don't really use or care about the manifold structure, you're going to have a difficulty connecting with those very important ideas. So that's where geometric control theory comes in. And so what happens here with these examples is there's another kind of thing other than coordinate independence that you want, and that you want your system to be independent of how you represent the appearance of control. Okay? Because the way to think about it is these are two systems where control enters the equations in a different way, but it's not materially different because it produces the same trajectories. Okay? So you don't want just coordinate invariance, but you want invariance in the way that control enters your system. And the way that you would say that is you want feedback invariance. So feedback basically means, I will not define it precisely, feedback invariance has to do with studying the invariance in the way the system, the way control enters the system.
Sorry,
Yeah.
this might be silly, but
No,
I
no.
just don't want to lose you. So, the way you think about this is basically two systems for you are equivalent, if I'm right in this. If basically there exists a control for this one, and there's another control for this one, such that the trajectories are the same.
It's hard to say that exactly, which is why I kind of don't want to go down that road. That's certainly one way to talk about it. That's kind of what you'd like at the end of the day, maybe.
Right. I just want to see in this.
Yeah. So in your head, that's a safe way to think about it in terms of this discussion that we're having right now.
For this one, another one for this one.
Essentially, they have the same trajectories. So there's some mapping between the controls for the two problems,
Exactly.
right? Yeah, exactly. Okay. So that's a safe way to think about this for the time being. Okay.
I just want to know.
Yeah, the picture.
Same trajectories.
Yeah, when you talk about feedback equivalence, there's lots of different notions of feedback equivalence, and that's a very, very weak one. And in reality, people don't study that one because it's virtually impossible to understand. But in fact, what we hope is that the methodology that we're developing here will get very close to having exactly that kind of invariance. Okay. So we want not just coordinate invariance, but feedback invariance. Okay. So coordinate invariance you get from geometry. Feedback invariance is less easy to get at. Okay, and I want to make sure that we all understand that we're not studying those. Okay, so this has to do with finding invariance, like you would study invariance in algebra. Okay, invariance of a system. We are absolutely not interested in that. That problem's way too hard. Okay, and you can do lots of interesting things without having to answer that question. Okay, so this has nothing to do with method of equivalence. Sorry, that wasn't a typo. But I actually spelled it right. Okay. All right. So does that sort of give you some idea of what I'm interested in here? Is this slightly clear? Okay. Without going through a huge list of examples, and without also having thought about this yourself independently for a while, it's not exactly easy to understand what the problem is here. I will grant you that. But this is maybe a place where you can enter that discussion. Okay. All right. So, how are we going to do this? Well, let me give you the sketch of how we're going to do this first, so that you have some idea of where we're going. And then when we have that, then we can start getting a little bit specific. All right, so the idea is this. If you have a system, so that was motivation, I guess this would be introduction. Okay. And if you're given a system like that, okay, so let's call this data. Okay, so it's described, a system like that is described by three things: a manifold, a control set, and this function f. Okay. All right, so let's think about this in a slightly different way to get some idea about one direction in which we can start thinking about things. Okay, so let's think about this question a tiny bit, although we've talked about it already. Okay. So we have some control function u of t. Okay, we plug that in and we get now a time-varying vector field. Okay, so let me call this vector field f sub u, and I think actually the way I do this is super u. Okay, and so this now is just going to be a vector field or tangent space valued function of t and x. Okay, so let's suppose that time, so it would be a good chance for me to introduce the kinds of notation I'm going to be using. So this will be, that's a math BBT, this is an interval. Okay. All right, so you have a time-varying vector field like that. Now, if you make suitable assumptions, okay, and now isn't the time to talk about those, okay, but if you make suitable assumptions on f and u, okay, the differential equation possesses solutions uniquely determined by their initial conditions. So it satisfies the standard existence and uniqueness theorems. Okay? All right, good. All right, so what we want to do is we want to look at this in a slightly different way. Rather than thinking of this as being a mapping, rather than thinking of a time-varying vector field as being a mapping like this, what we will do is we will think of a time-varying vector field as being a vector field valued function of time. Let's call that thing f hat. Okay, so f hat is going to take time, and what it will do is return for you a vector field, and it does it in the obvious way. And so regularity is something that we're going to be very concerned with here. We want to develop a theory that can handle any meaningful kind of regularity of vector fields, and we will talk about that in some detail. Okay. So by this, I mean vector fields of class C nu. Okay, and I will specify what nu is subsequently. So we're going to talk about all kinds of possible kinds of regularity, but this is my notation for vector fields. Okay, so what this just, of course, just means you have this vector bundle, which is the tangent bundle, and these are the sections of class C nu. Okay. All right, so you have this map f hat, which has the obvious definition. So it's a vector field. Okay, so it takes values at a point x. All right. Okay, so what we want to do, instead of thinking of mappings like this, okay, and what's wrong with this? What's wrong with this is the following, that this function fu, it really depends on this very specific choice that I've made here, okay? And so this choice here involves choosing a specific way in which the u's enter your system of differential equations, okay? So what you want to do is you want to kind of write this down in a way where the dependence of these equations on u is pushed into the background, okay? You know, in exactly the same way that by saying you have a vector field on a manifold, in your mind, although possibly when you do calculations, you work with a set of coordinates, in your mind you're imagining this as being a geometric coordinate invariant entity. So we want to kind of do the same thing with control. Okay? All right, so what we want to do is we just want to alter the way that we think about this a little bit so that it provides a way of thinking about it which can be maybe adapted to a feedback invariant way of formulating things. Okay? So what we want to do is we want to skip this intermediate step here. Okay? This intermediate step of saying we prescribe a control u of t.
So,
Okay?
Andrew, is there a measurable issue of restriction from one representation to another representation?
Say it again.
Is there a
You mean are you heading for the question is when are these two ideas equivalent?
That's right.
Yeah, we'll get there for sure. Very important question, and it sort of explains where a lot of the technicalities are going to come from. Yeah, absolutely. But we're going to talk about that. Yeah, and that's about what I'm going to say. Okay. So instead of this, okay, simply consider. Okay, a time varying vector field. Okay, x. Okay, so x now is going to be a map from t into here. Okay, such satisfying. X of t, so for each fixed t, the vector field takes values in the set of all vector fields that you can get like this. And so what do I mean by that? So I'm being a little, I want to make sure we understand I'm being a tiny bit imprecise here. Sometimes I'm going to, and really, if I was faithful to the way I do this in real life, when I prescribe a control as a function of time, I write it as mu, not u, to distinguish the fact, mu from being a function, taking values in C to being a point in C. Okay, so maybe I should do that. All right. So here I'm going to write u, okay? And so fu of x is f of x u. Okay, so these are now constant time invariant vector fields, just regular plain old vector fields. Okay? So what I'm going to do now is I have this collection of vector fields, f sigma, okay? This collection of vector fields, okay, it's the way it's defined is it's being indexed by u, okay? But once I have it, okay, it's just a collection of vector fields, and it doesn't really care what the index u is that labels an element. So that's just a set of vector fields. Okay, so the point is, rather than prescribing an equation like this, what we're going to do is we're going to talk about sets of vector fields. Okay, so we're going to take this f sigma and we're just going to replace it with an arbitrary family f of vector fields. Okay? And I don't care about labeling them like that. Okay, and then like you said, Sarah, the questions of that intermediate labeling and whether you start with a family of vector fields. So, you know, one of the questions that comes up is you can go from here back to a representation like this, and you can go from a representation like this back to here, and when do those two things commute? Yeah, it's an important question. Okay, and we will get there. All right, so where have we gotten to? So what we're going to do is we're going to replace x dot equals f of x u with a family of vector fields f of some regularity u. Okay, and then trajectories. Okay, so over here I told you how you get trajectories from this setup. Okay, how do you get trajectories from this setup? I will be writing the word time-varying vector field a lot, so I'm going to abbreviate that with TVF. And I think actually I've been known to do that, so I'll try to stick to that. Time-varying vector fields. So our integral curves are time-varying vector fields, and we want to think of a time-varying vector field as being a map into that. Okay. Now, of course, you know, I didn't prescribe the assumptions here, which ensure that you have existence and uniqueness of integral curves or trajectories for these systems. Okay, but they're known. Okay, so and we'll talk about them. Okay, so in this setup, it's relatively standard to give assumptions on U and F so that you have standard existence and uniqueness of trajectories. Okay, now if you're just going to now be talking about a time-varying vector field valued function, you have to replicate that. So you have to come up with some attributes that you're going to give to this map X, which will ensure that it has integral curves. And I'm not going to tell you what those are right now, but that's one of the things we're going to spend a great deal of time doing. Okay? All right, so that's one way in which you go from standard control theory to this slightly different way of thinking about a control system. It's a family of vector fields, okay, and then you want to talk about time-varying vector field valued functions with values in that family of vector fields. Okay, does that make sense? Okay, and the point is here is that you've eliminated this intermediate step of prescribing a control. All right, now that's one part of the sort of tautological control theory framework. And that part is relatively easy to understand why we do it. Okay, apart from the fact that this step right here, this prescription of the attributes that you need, that's hard now, okay, as we'll see. Okay, so that's an impediment to using this theory, and you have to do some work to make that function, right? But it's relative, yeah.
Is this like somehow, could I somehow think about this as a, sort of a differential inclusion?
No, but thank you, and we'll talk about differential inclusions.
Yeah, just sort of as
yeah, absolutely, yeah, that's right, yeah.
I'm sort of missing something.
Yeah, no, absolutely, I'll talk about that. Thank you for reminding me, I would have forgotten.
Okay.
Okay.
I'm just trying to understand this representation. So the way I see this is this. So rather than looking at the mapping from Tx to gamma m, what you do is you fix your T, and then the image is going to become the set of all maps from X to T of m, or from M to T of m.
Vector fields, yeah,
Right?
yeah.
But is it the same? Is gamma u of T of m?
So it's not a set of all maps from M to Tm, right? Because a vector field isn't an arbitrary map from M to Tm. It has, when you evaluate X at a point X, it has to be in the tangent space at X, right? But it's a set of all those things.
Okay.
Yeah. That's right. So it's this is a family of mappings. Yeah. So this is a gigantic, infinite dimensional thing. Yeah. That's one of the difficulties. Okay. All right. So this kind of arrow from standard control theory to this kind of a picture is relatively easy to understand. Okay. The other arrow that we're going to follow for these systems is not so easy to understand why you would ever want to do that. But nonetheless, we're going to do it. Okay. And there's no easy way to really comprehensively explain why this is a good thing to do. And in fact, I can't even really compelling you to convince you that it is, because there's still lots of work to be done with the ideas here. But it looks extremely promising so far, so that's all I can say. So this is going to seem to you to be unsatisfying, and so if you are impatient, this is going to be hard. Okay? But suck it up. Okay. All right. So what I'll do is I'll kind of, I'm going to be much more precise about these things subsequently. So the purposes here are really just to be explanatory and to give you some idea of where we're headed. Right? So this isn't going to be a very satisfying discussion. All right. So. Okay, so we work with things that are kind of just locally defined. Okay? All right, so what I mean is, rather than talking about that, okay, I'm going to use the same symbol, script F, and we're going to talk about something like this. Okay, so I have, for every open subset of M, I have this object f of u. Okay, and f of u will be a collection of vector fields on u. Okay, so it's exactly this, done for every open subset of M. Okay, and then you need some compatibility condition here, and I'll save that for when we actually define this correctly. But the point is that you deal with things that are locally defined. What's the value of that? Well,
Andrew,
yeah,
I was thinking you might want to use uppercase U, capital U, just so that.
that is a capital U.
Oh,
Yeah.
I just.
But it may not look like it, but it is, yes.
Yeah, because you
Yeah.
need the codex.
I will never be, I will not, the whole point of tautological control theory is to eliminate control, so it's not going to come out much.
Okay, that's fine.
Okay. So I'm going to use vague words like something, rather than actually saying what I'm talking about. So we're going to say something is globally defined. Okay, so I have right? So one way that you can do this is you can just define these, you can choose something global like this, so like I did over here, okay? And then you can simply say that f is defined by restricting all of these things to u, okay? That's one valid way of arriving at a specification of an f of u for every open subset of M, okay? But there's other ways of doing that. So, some useful things are not globally defined. Okay, let me give you an example. All right. So let's suppose that I take a distribution on M. Okay, so this means a prescription of the subspace dx at every point x and m, and these have to fit together smoothly in some way. Okay? So I see new prescription, so let me just tell you the words, I don't want to write it down. When I say that we have a C nu distribution, what that means is around every point x and m, there is a neighborhood and a collection of C nu vector fields defined on that neighborhood, so that this is the span of those vector fields at every point in the neighborhood. Okay, so that's what C nu means. All right. Okay, so I can define okay, f sub c of u will be the C nu vector fields on u such that x of x is in dx over x in u. Okay, so these are all the vector fields on U, which take values in D. Okay? This is not a globally defined object in that sense. Okay, so there does not exist a global set of vector fields, so that fd of u is just the restriction of all those vector fields to u. Okay, if you don't see that, and if you're not used to thinking about this stuff, it may take a second, but think about it. Okay, and so now I'm just going to tease you. Okay. for smooth or real analytic distributions. Oops. Okay, so there's this construction that we will talk about called sheafification. This guy is the sheafification of something that's globally defined, and the globally defined thing is simply the set of all vector fields on M taking values in D. Okay, so then you can, that is not a sheaf, but you can sheafify it, and the resulting thing is exactly FD. Okay, that's an easy thing to prove using bump functions and crap when when the distribution is smooth. When the distribution is analytic, that's not easy to prove. You have to use Cartan's theorem A for analytic sheaves. Okay. And so also to give you a bit of context, so FD is just not global in general. If we're talking about holomorphic things. So we will also talk about holomorphic, meaning complex analytic objects as well. They provide a little bit of a setting for real analytic things, and also gives you some context like this. Okay.
So
Yeah.
it's easy for infinite because that's the construction. I remember before with inductive limits and things like this.
No. So what you really have to show, I don't know exactly what you mean by inductive limits in that case.
You kind of restrict to.
Yeah. So so what you have to show the sheaf property that if you have an open cover of an open subset and something defined on each of the elements of the cover, and they agree, just on the open cover, and they agree on overlaps, then they extend to something global. Yeah. So.
But that part, but doesn't that contradict the fact that FD is not globally defined? That kind of thing, no.
No, FD is. Let me.
It's not globally.
Yeah. No, that does not contradict that. Yeah. Remember that restriction of things agreeing on overlaps is a restriction, right?
Mm-hmm.
Yeah. So when you extend something globally, by having compatibility on overlaps, that's enough to make the object you're talking about be globally defined. But that doesn't mean that FD is globally defined. Yeah. Okay. So these are all things we're gonna talk about. Okay, and if you ask me, this part of tautological control theory will prove to be the most important part. This is an essential part, okay, but it's kind of easy. It's not. The idea is easy. This idea does not come very easily, but I think it's deceptively useful. Right? Okay, so now. What we will do is we'll stop. What time is it?
Almost done.
Almost done. Okay. So we'll stop the introduction and we'll get down to business. Okay. All right, so what we will do is we'll start talking about the problem of giving enough structure to the space of, I erased what I wanted to refer to the space of vector fields that we can talk usefully about time mappings from time into the space of vector fields. So what kinds of properties should you have of those vector field valued functions of time? Well, what you need, of course, but what you need is a topology on the space of vector fields. Okay? So, and we're going to be topologizing not just spaces of vector fields, we're going to be topologizing spaces of mappings between manifolds, vector fields, in fact sections of vector bundles, which include, as special cases, vector fields and functions. Okay? And this is going to take a while. Okay. But the nice thing about this is two things. At the end of the day, after the long, rather complicated discussion, we will have some tools at our disposal for talking about spaces of these guys for many different regularity classes. Okay, we're going to talk about finitely differentiable things. We're going to talk about things that are Lipschitz. We're going to talk about things that are smooth. We're going to talk about things that are real analytic and holomorphic. Okay, and we're going to do that in such a way that you can very often state the important theorems all at once. So in other words, you can state the theorems with an arbitrary nu, and that's nice. Okay, but it takes some work. All right. So just notation for the time being. All right, so nu for us here will be m, and so let me write it all down. Okay, so these are the regularity classes that I'm going to consider. M, okay, is a non-negative integer. So these are finitely differentiable objects. M plus lip means that it's m times differentiable and its mth derivative is Lipschitz. Okay, so when m equals 0, that's Lipschitz. Infinitely differentiable, real analytic, and holomorphic. Right? So whenever I write nu, and I don't tell you what it is, it can be any of these, with the possible exception that when I'm talking about real things, I'm not talking about holomorphic. Okay. So, okay, so C nu. So I apologize, my nus look awfully like R's. So if there's any confusion, let me know. So if I have two manifolds, and so the manifolds here have to have, of course, the appropriate regularity, and I therefore will talk about manifolds that are infinitely differentiable, real analytic, or holomorphic. Okay, so I'm not going to talk about manifolds that are finitely differentiable. That seems sort of pointless. Okay. All right, so our manifolds will be very regular, but our mappings may have differentiability in one of those two classes. Okay. We will talk about sections of vector bundles. Okay, and two particular special instances of this that will concern us are when the vector bundle is the tangent bundle, so these are vector fields. And then okay, the functions, we can alternatively think of a function as being a section of the trivial bundle, the trivial line bundle, if you want to use fancy language. Okay. All right, so that's notation. All right, so we're going to topologize all of these spaces, okay, and for all of these classes of regularity. All right, so what do you need to do that? Well, let's just sort of think intuitively for a second, because I'm going to take a gigantic detour first, right off the bat. So if you want to topologize, let's say, C-infinity mappings, okay, well, you need to measure the closeness of a mapping and all of its derivatives, because it needs to be close in C-infinity, okay? So the point is that you need a way of measuring closeness of derivatives, and there's a bunch of ways to describe how to do that. You can do it locally in coordinates. You can do it globally, which is kind of my preferred way to do it, although I'm going to be describing, I think, for each of the, well, for this case, I think we're going to look at 4 equivalent descriptions of topology here. Okay? So there's lots of ways to do that. Locally in coordinates, but the way that is often most useful in practice is to kind of come up with distance functions on spaces of derivatives that allow you to use sort of globally defined semi-metrics. And so that's what we're going to do to talk about that. And then similar ideas apply for sections of a vector bundle. Okay? All right, so what we need to do is we need to have spaces of derivatives, okay, of mappings between M and N, and then we need to find a convenient representation of those spaces of derivatives, and then we need to put metrics in just the normal metric space sense on those. Okay, so we have a bit of work to do. Okay. So we'll talk about jet bundles. So jet bundles are just spaces of derivatives. Okay. I will simply not, I don't want to take the time to do this super precisely. So if you have any issues with what I'm saying, you'll have to go off and do a little bit of extra work. I'm basically going to give you the intuition here. Okay? So if you take so we're going to just work with the real case here. There's a corresponding, you can talk about holomorphic jets. There's nothing preventing me from doing that, but we're not going to use them. All right, so we're going to talk about real manifolds that are smooth or real analytic. Okay, so let's let X be in M, Y be in N. Okay, and I'm going to let J, K of X, Y of M, N, okay, be the set of equivalence classes of locally defined okay, so when I say that, I mean these mappings may only be defined from a neighborhood of X to a neighborhood of Y. They're all going to map X to Y, but they're not necessarily going to be globally defined. Okay, equivalence classes of locally defined mappings in neighborhoods of X and Y that agree, okay, that first of all map X to Y and agree at X to order K. Okay, so the most concrete way to say it is that if you write the mappings in coordinates, their first K derivatives agree. All right. Okay, so right? And the JK is the disjoint union over all x and y and m. This is what's called the kth jet bundle. Okay, it has lots of structure. It has a differentiable structure. It has, okay, so if you, there's an obvious mapping from an element here to m, which simply maps you to x. Okay, and then there's a mapping that maps you from an element here into n, namely y. So you have projections from jk into m cross n. Okay, and you also have projections into m and n. But over m cross n, that's a fibered manifold, and there's some nice algebraic structure. If you fix a k, okay, so you have those projections. You also have projections, so maybe I'll introduce those ones. Okay, so we have projections pi k l of j k of m n to jl of m n when l is less than or equal to k. Okay, and it just forgets the fact that it's the derivatives agree up to order k and only remembers that they agree up to order l. Okay. All right. So there's some nice algebraic structure. And I'll describe it to you because it's going to be kind of important for having any idea about some of the representations of jet bundles that I'm going to talk about. And I forget exactly what this mapping is. It doesn't matter for our purposes here. So we have a mapping from S. Okay, so it'll also give me a chance to introduce my notation. Okay, so S K of T star M tensor Tn. Okay, so T star M, of course, is the cotangent bundle. This is the degree k symmetric tensors on this vector space. Okay, so you can think of this as being polynomial functions on and I will need to fix an x and a y. Okay, so one way to think of this whole thing is degree k polynomial functions on the tangent space. Okay, real valued. Okay, and then by taking the tensor product here, it takes, one way to think of that is it takes the real valued things and gives you things taking values in here. Okay. All right. Okay. So what we're interested in here, and I'm not going to explicitly describe the structure for you, but take things that agree to order k minus 1. Okay. Sorry, take things that agree to k and consider a mapping from here to here. So a point, so two elements here will have the same image here if they agree to order k minus 1. Okay, so what we're interested in doing is we're interested in fixing a point here, studying the pre-image here. Okay, so all derivatives of order k that agree up to order k minus 1. Right? That's how you should think about what we're trying to do here. And sort of the exactness of this sequence in a certain way tells you that the set of things, the derivatives of order k that agree to order k minus 1 is this. Okay, and what's this? So think about this for a second. So these are degree k polynomial functions on Tm taking values in here. Okay. The way to think about that is it's like a Taylor coefficient. Right? This is the kth order Taylor coefficient, right? Because what's the kth order Taylor coefficient? Is just the kth derivative, right? So this is really a space of kth derivatives. That's how you should think about that. Okay. So this says that when you fix the first k minus 1 derivatives, the set of all kth derivatives you can think of as being that. Okay. Now, What's not true is that JK is itself, sorry, so JK is the set of all kth derivatives. It's not true that there's a natural product structure on here of, you know, S1, S2, S3, S4, and so on, all the way up to K. There's no product structure here. This is really the only structure you have, is if you fix something here, you get some structure here, and it's that, okay? So this gives you some structure here, but not a lot. And in fact, one of the things we're going to try and do is we're going to try to give this space a nice product structure. Okay. All right. All right, but to do that, we're going to think about these guys in a slightly different way. All right. Okay, so all of this entire idea here can be specialized to the case of not manifolds M and N, but you know, N is a vector bundle over M, and you're going to talk not about arbitrary mappings between M and E, but sections. Okay, and we call that JKE, and so this thing lives inside JK of ME. Okay. All right, and then we have an additional special case where we're talking about real valued functions. Okay, so so this is going to be kind of an important object for us. Okay, this means you take jets of functions at x which take the value 0. Okay, so we're going to fix in this space here. We will fix all functions to take the value 0. Okay, so I think I'm kind of out of time. So next time what I'm going to do is I'm kind of going to glue all of this together, and we'll start talking about how to simply represent jet bundles. Okay?
And
Yeah.
just so that I get kind
Sure.
of the kind of, so you just put basically a topology on gamma RTM, right?
Yeah.
Right. And so I'm just trying to see roughly speaking why jet bundles. So you wanna, you sort of need a connection of some sort, right?
Yeah, that's where we're
And
going to
so
go.
you're gonna take sections of E to J1E and take connections. Is that the? Or-
So the connections will give us decompositions of these jet bundles into things like this.
Mhm.
Yeah. Okay. That's kind of where we're going here. And the point is that when you have this kind of structure, it's more easy to understand the metric structure of jet bundles in terms of metric structures on, say, M and N. Yeah, that's kind of where we go. And the point is kind of if you have metric structures on M and N and you choose connections, then everything has a nice metric structure. And then when you have a metric structure on the jet bundles, then you can talk about topologies for the spaces of sections. Okay? All right. So next Monday. Thank you.